Hi everyone. In this video, we will explore the development of early atomic theory from ancient Greece through John Dalton in 1809. The goals of this video are to help you understand early developments in our understanding of the composition of matter and to understand the evidence that led to Dalton's proposed atomic theory. We will also begin to use experimental evidence to make a claim about the behavior of matter, similar to what you did with the calcium carbide demo in class the other day. One of the earliest recorded theories we have about the existence of atoms comes out of ancient Greece and a philosopher by the name of Democritus. So this was a theory that's completely based on reasoning and logic. There's no experimental evidence to back up his theory, but basically what he said was, or what he was thinking is, that if you have a rock, right, and I take that rock and I smash it, I'm going to end up with smaller rocks. And I smash those rocks and I get even smaller rocks, etc. And I can keep going on and on and on. Well, eventually there's going to come a point where I can't smash the rock any further. And rocks are different from air and they're different from water. And so what Democritus said was that everything is composed of these atoms that are tiny and that are physically indivisible from each other. Between the atoms is empty space. They're indestructible and always in motion. And there's an infinite number of atoms and an infinite number of types of atoms that differ in size and shape and other properties. And essentially what he said was that they interact mechanically. Think about like Velcro or gears or a ball and socket joint, something along those lines, which actually isn't bad for a theory that's coming out of no experimental evidence whatsoever. So we're going to fast forward a little bit through the Dark Ages and into the Age of Reason, and come up in France, a chemist by the name of Lavoisier, in 1774. And he was making very careful observations of reactions, so starting with reactions and ending up with products, and making sure to very carefully keep track of what he has and what he started with. So what he ends up with, what he did, was he took a reaction where he took A plus B, I don't care what it is, and he created C plus D. And he did this in a completely enclosed container. And what he found was that the total mass of the reactants always equaled the total mass of the products, taking into account things like gases that are formed. So if you keep it in a closed container to enclose all the gases, the total mass of the reactants has to equal the total mass of products. Always, no matter what, which came to be known as the law of conservation of mass. Which in terms of chemical reactions is still true today. So moving on into, still staying in France, Proust in 1799 was looking at the composition of compounds. And so what he found was that if I take, for example, NaCl, sodium chloride table salt, NaCl is always about 30% sodium and about 70% chlorine by mass, no matter where it comes from. If I get it from the Dead Sea, if I get it from the Great Salt Lake, wherever, it doesn't matter. No matter where it comes from, sodium chloride always has the same composition by mass. And this is true of any compound that you look at. So what that suggests, or what that says, is that every chemical compound is made up of a fixed ratio of elements, right? So a fixed ratio of elements. And this became known as the law of definite proportions. And then while that was happening at the same time, John Dalton in England this time was looking at compounds that are made of the same two elements. So for example, if I have two compounds that both contain carbon and oxygen, right? So compound number 1, for every 1 gram of carbon, contains 1.33 grams of oxygen. And compound number 2, completely different properties. For every 1 gram of carbon, contains 2.66 grams of oxygen. So if I look at the ratio of oxygen to a fixed amount of carbon in each of these, it comes out to there's 1 oxygen for every 1 carbon here. So for every 1 carbon, it looks like there's 1 oxygen. And for every one carbon over here, 1 unit of carbon, it looks to be there's 2 units of oxygen over here. So what that means, or what that suggests, is that we have fixed small whole number ratios, right? So I'm comparing the amount of oxygen that combines with a fixed amount of carbon, and it varies by a small whole number ratio, 2, 3, 4, something along those lines. So this is called the law of multiple proportions. Right, and taking all of this experimental evidence together says we come with Dalton's atomic theory. And so Dalton's atomic theory takes the law of conservation of mass, definite proportions, multiple proportions, everything else that we know about the composition of matter, and puts it into these 5 postulates. So in these 5 postulates, says that matter is made of tiny particles called atoms. And atoms of a given element are identical in size, mass, and other properties, and different elements differ in size, mass, and other properties. They cannot be created, destroyed, or subdivided. Atoms of different elements combine in whole number ratios to form compounds. And in chemical reactions, atoms are combined, separated, or rearranged, but they're not created or destroyed. So pieces of this come from different theories, right? We can see definite proportions and multiple proportions here in this postulate. This postulate is the conservation of mass part, and this is the idea that carbon atoms behave identically and sodium atoms behave identically, et cetera, et cetera. So looking at these 5 postulates, this is pretty good for 1809, given the evidence that Dalton had to work with. As we know today, there are a couple of these that are a little bit not quite right anymore. So in preparation for a class tomorrow, we want you to think about which part or which whole postulates or which parts of postulates do we know today are no longer true? What seems fishy to you in this theory based on what you know from your prior knowledge or from your previous experience? Okay, so give that a thought, write down some thoughts, write down some of your thoughts in your packets, and we'll see you in class.